Okay, so let's start our class. So first of all, today we're going to just doing the review for the whole unit 3, and then we're doing the practice exam before the Wednesday exam. Okay. And right now I don't have your the study guide, the worksheet that we work on Wednesday, but I'm going to send the key and the another worksheet, exactly the same worksheet to you just for review things. Okay, just for the review. And also, if you don't haven't turned in the worksheets that we did on Wednesday, you don't have to turn in today. Okay, so let's turn in next time. So when we meet, okay. And you can using those stuff for the review. Okay, so let's start review the exam 3. Unit 3. Unit 3, we start to talk about the molar mass. Okay, try to figure out what is the molar mass, or we call it the mass of a compound. First, we talk about what is the concept for mole. Okay, mole is a really big number, right? It's a 6.02 times 10 to the 23rd, and we call this Avogadro's number. Avogadro's number. So this is a really big number. Okay, I mean the meaning of this number is just 1 mole. So mole concept is just a group of number, just like a pair and dozen. So this is a mole concept we talk about. Okay, yeah, because once you have 1 mole of those compounds, those doesn't matter is an ion or atom or molecule, then you can just based on the mole based on the atomic number, atomic mass, average atomic mass in the periodic table to figure out the molar mass of the elements. So the molar mass is another concept we talk about. The molar mass is just the mass of object, one mass of 1 mole of the object. So that is the concept. Okay, so if we have 1 mole of those molecules or ions or atoms aggregate together, what is the mass? And that is the molar mass. Okay, so molar mass you can find from the periodic table. Okay, and you can based on the periodic table to figure out the molar mass. And also we talk about what is the molar mass of a compound. The molar mass of the compounds generally it just give you a formula like a sodium carbonate or copper 2 sulfate. Okay, so generally what you need, you just based on how many atoms of those elements inside of the compound, and then you add them together, and that's it. The first one, obviously you have 2 of the sodium plus 1 of the carbon and 3 of the oxygen. This is for the first one. This is for, so if you know the molar mass of each of the elements, you can find it from the periodic table. So you can add them together. That's going to be the molar mass of the sodium carbonate. Doing the same thing for the copper sulfate. Okay, so this is the same thing. Just add them together, then you will find the molar mass of those stuff. But the very important is, okay, when you write those units, every number has a unit in chemistry. Okay, yeah. So the molar mass, the unit of the molar mass is gram per mole. Okay, so that is why if you look at the unit, you know, okay, the unit should be using gram of something divided by mole of something, then you will got the molar mass, right? Gram per mole, or you can call the gram per 1 mole, which means 1 mole of this object is equal to how many gram? Okay, so you can just also using the molar mass as a conversion factor, because you can convert this mass to the moles. The molar mass telling you 1 mole of the object equal to how many gram. So if we have 0.5 moles of the object, then you can convert that to how many gram also, right? So conversion factor, you can using the molar mass as a conversion factor between mass and the mole. So that's why later we talk about how to convert mass to the mole. Okay, so how to convert the mass to the mole, how to convert the mole to the mass. Last time we talked about, okay, better to remember the equation. It will save you quite a lot of time, especially when we talk about unit 4, we are still going to using the mole mass conversion, okay, to each other's. So mass of the object should be equal to mole of the object times the molar mass, Okay, why doing so? You can base on the unit. You see, moles unit is mole, and your time molar mass. The molar mass unit is gram per mole. You see that this mole and this mole will be canceled. So then the unit will be just a gram, which means it's a mass. So that is why mole times molar mass will give you the mass. So this is the equation, mass equal to mole times molar mass. Okay, and then the mole will be just the mass over molar mass. Okay, mass over molar mass. It's doing the same thing. Okay, so those two equations, I recommend and I strongly recommend you remember this. Okay, mole equal to mass over molar mass, mass equal to mole times molar mass. Okay, and then it will save you quite a lot of time when you do the conversion. Okay, and also we talk about the Avogadro's number. So Avogadro's number is talk about if we have a 1 mole of object, how many atoms for this object? How many atoms for this substance? Well, they have a 6.02 times 10 to the 23rd of those atoms. If it's talk about atom, then that's talk about elements, then that's atoms. If we talk about molecule, then that's a compound. But if you talk about ions, that could be ions. So doesn't matter it's atom, molecule, or ions, they are all equal to 6.02 times 10 to the 23rd. And this is 1 mole of the object. Okay, doesn't matter what kind of 1 mole of 1 mole of water, 1 mole of the copper, 1 mole of oxygen, doesn't matter what kind of things, they all equal to 1 mole. Okay, so now this is also a conversion factor. You see, this is also a conversion factor. 1 mole and molecule numbers as a conversion factor. So we can also, based on this, to figure out the mole and molecule number conversion. Okay. So now we know 1 mole. If we want to find the mole of the molecules, mole of the object substance, then that's gonna be equal to molecule number divided by Avogadro's number, which is 6.02 times 10 to the 23rd. Okay, so mole divided by molecule number divided by Avogadro's number, you got a mole. Or if you have the mole, you try to figure out the molecule number, that's going to be just a 6.02 times 10 to the 23rd, and you multiply the mole. Then you got the molecule number, which means 1 mole of the Avogadro, 1 mole of the compound, then that's 6.02 times 10 to the 23rd. If we have 0.3, then you times 0.3 times Avogadro's number, you will got how many numbers for the 0.5 moles, half moles, which is going to be a 3.01 times 10 to the 23rd. Okay, so the Avogadro's number multiply the mole number will give you the molecule numbers. How many molecules for those compound or substance? Okay, so that is why we have the conversion between mass to the mole and also to the molecules, molecule numbers. Okay, so those three can convert to each other's, but the intermediate part is the molecules. So if you want to convert the mass to the molecule number, well, you have to from mass to the mole, and then convert the mole to the molecules, and then you can figure out. Or if you want to convert from molecules to mass, again, you need to convert that to the mole first, and then from mole to the mass. We did a worksheet on this. Okay, yeah. A lot of people still have no idea how to make the conversion, but I think the best way to get this map in your cheat sheet. And at least you can base on this map to figure out where to go. Since, okay, if your question has the molecule numbers, asking what's the mass, then what do? First say, okay, what's the first step we're gonna do? Well, first step, you're gonna convert that to the mole. And then you can from mole to the mass. Okay, but those mass and the mole conversion, the intermediate part is the molar mass, right? You need a molar mass to convert from mole to mass or mass to mole. Molecule number to and mole, you need Avogadro's number, 0.602 times 10 to the 23rd. Okay, so if you know this, then generally you know how to solve the problem. And by the way, for the Wednesday's exam, you can still have the half-page cheat sheet, okay, front and back, so you can work on and try to figure out what you really need to put in there. I mean, since today we're doing the review, and also we're doing the practice exam. So after this, you will know which part you're still not good at, and what's the information you're gonna put majorly in your cheat sheet. That makes sense, right? Okay. All right, so this is the conversion between mass, mole, and the molecules. Okay, mass, mole, and the molecules. And the next part we talk about is the mass percent or percent composition. Or the mass percent. Percent composition, mass percent, it just talk about the single elements, like you have a sodium carbonate. What is the mass percent of the sodium? Okay, so mass percent, I mean, since talk about the mass, so that means it's just a mass of the sodium and divided by the total mass of the sodium carbonate. Then this gives you the mass percent of the sodium, right? So the sodium percent generally is just a sodium mass percent, which is the mass of sodium divided by the total mass of the sodium carbonate. So this is how we got the mass percent. Okay, yeah, the mass percent. If you're theoretically, you can just based on the formula to figure out the mass percent, which is you can using the molar mass to figure out the mass percent. Use a molar mass of the sodium, you time 2, since this compound has 2 of the sodium. So the molar mass of sodium times 2, and then that's going to be the mass of the sodium. And you divide by total mass of the sodium carbonate, which is the total molar mass of the sodium carbonate. And then you time 100%, you will got the mass percent. Okay, yeah. You will got a mass percent. So this is the mass percent, but also you can also based on the lab result. You can also using based on the lab result to figure out the mass percent. Okay, we did several lab talking about this. We try to figure out what is the water percent in the hydrate. Okay, then that's going to be the mass of the water that you got from the experiment and divided by the mass of the total hydrate and figure out the mass percent. So generally the mass percent can based on both things, which is mass of the sodium divided by total mass of sodium, or molar mass of sodium divided by total molar mass of sodium carbonate. Okay, so those are both things can figure out the mass percent. And you time 100%. Okay, so this is the mass percent that we talk about. But if you look at the equation, you see, if you look at the equation over here, this equation actually is also give you some relationship between mass of the sodium carbonate, and the composition, the percent, mass percent. So you see, so if we know how many sodium carbonate do we have, and also we know what is the sodium percent in this compound, and how to figure out what is the mass of sodium. Well, this is the equation that you're looking for, right? Yeah, we did this worksheet on this. So the mass of the sodium actually is just equal to the sodium percent, right? Sodium percent, and multiply the total mass of the sodium carbonate. Okay, what I'm writing here is the math. Okay, it's a math. It's just based on the equation to solve the problem, like x equal to y divided by z. So y should be equal to x multiply z. Okay, or z should be equal to y divided by x. I mean, that is the math problem. This is algebra. This is not the chemistry part, right? So you based on this equation, you generally can figure out the 3 things. Okay, based on this equation, if you know any of the 2 unknowns, 2 parameter, you should be able to solve the 3rd one. Okay, just based on the equation set up like this. Okay, yeah. So if you want to figure out the mass of sodium, which is on the top part, which is y, y should be equal to x times z, which is sodium percent multiply the total mass of sodium carbonate. Okay, so you based on this, you figure out these equations. And this is makes sense, right? If you know the total mass of the sodium carbonate and you multiply what is the percentage of sodium carbonate, sodium, then you should be able to figure out the mass of sodium. Okay, for example, if you know the sodium percent is 21.2%, and you know we have a 200 gram of the sodium carbonate, well, then what is the mass of the sodium? obviously you should be using the 20 gram, 200 gram of the sodium carbonate, and you multiply the sodium percent for this compound, then this is 21.2%, then you should figure out what is the mass of sodium. That's it. Okay, that's it. So this is how we figure out the mass of sodium. And also based on this equation, you can also figure out, okay, if I know the percent of the sodium, and also we know the mass of sodium, how can we figure out the total mass of the sodium carbonate? Well, obviously, you try to figure out the Z. The Z will be equal to Y over X, which means should be mass of sodium divided by the sodium carbonate percent, then you should be able to figure out the total mass of the sodium carbonate, right? So the total mass, that should be equal to the mass of sodium divided by sodium percent. Okay, so this is also another equation just based on the equation that we gave. Okay, yeah, we did this kind of the practice before in the worksheet. Okay, hopefully you still remember those. Yeah, if you forgot it, better to go back to double check. And once again, I'm going to send all the key and the worksheet to everyone, so you will have a time to review everything. And I believe I already returned the worksheet back to you. Okay, yeah, so you can work on, review those things. Okay, so this is the conversion. We try to figure out, for the mass percent and the percent composition and the mass percent. Let's take a break and then we will talk about something more.
very like very suspicious. It's very like I was like, what's going on? She didn't go through all the organization stuff. Oh, he's dead. So I was like, it's not for all. And then like I'm trying to do like so I'm running there. So I was like, I don't think when she told me to I can so it's the guy right here. And I was like, like he's like, I'm not gonna catch you. The horse is not moving. Not like mental.
Oh my God. Okay, so let's keep going. Let's keep going to review the things. Okay, next part we're going to talk about, okay, how come we got from the percent composition to figure out the empirical formula. Okay, how to got from the percent composition to the empirical formula. Okay, yeah. So generally, what do you do? Okay, if you try to figure out the empirical formula, and for example, we have the compound X. Well, let's see. If we try to figure out the empirical formula between the copper and oxygen. Okay, so you don't know what is the X and Y. So generally, you try to figure out what is the ratio between X and Y, right? You try to figure out, okay, well, this number versus this number, and we try to make those ratio as a whole number. Okay, this is the most important things. We try to make the ratio as a whole number. So X versus Y cannot be equal to 1.32121 versus 3.33222. Okay, so this doesn't work. You have to make as a whole number. Okay, so first of all, what do we do? Well, the question should give you the percent composition for the copper and oxygen, right? Either they're telling you what is the copper percent in this compound and what is the oxygen percent in this compound. So it will tell you one of this, okay? So you can base on the numbers of the percent of the copper and percent of the oxygen, and you try to figure out what is the mass of those compounds. So first you try to figure out the mass of the copper and try to figure out the mass of the oxygen. Last time we talked about, well, the best way to figure out, the easiest way to figure out the mass of the copper is just assume you have 100 grams of those copper oxide. You assume you have 100 grams of the copper oxide. Why? Because you see, you try to, if you want to figure out the mass of the copper or mass of those compound inside, you just need to assume if we know the mass of copper oxide and multiply the copper percent, we will get the mass of copper. So this is how you do. If you assume we have 100 grams of copper, your 100 grams of copper multiply the copper percent, you will get the mass of copper, right? So this is the easiest way to figure out the mass of copper. Well, then obviously, if the question do not telling you the copper percent or oxygen percent, they directly telling you the mass of oxygen and mass of the copper. Should we still need to find the mass of copper and the mass of oxygen? You don't have to convert that step, right? Because the question is already gave you the mass. So what we do, we first to find from the mass of the percent composition to the mass of copper. But if a question already telling you the mass of copper, then you just ignore the previous step, right? So you got the mass of copper and the mass of oxygen. The next part is you need to figure out the mole of the copper and the mole of the oxygen. Okay, you need got the mole of oxygen and mole of copper. This is the second step. How to do this? Obviously, the moles of the copper will be equal to the mass of copper divided by the molar mass of the copper, right? So you see, this is coming from the previous knowledge. And the mole of oxygen will be the mass of oxygen divided by molar mass of the oxygen. We're talking about copper and oxygen. We're not talking about the copper oxide, okay? So you just divide by the molar mass of the copper or molar mass of oxygen, okay? And then you got the moles. So in general, the empirical formula, you try to figure out the ratio of the empirical formula is actually, it's just a mole ratio between copper and oxygen. So actually, it's just a mole ratio of the copper versus mole ratio of the oxygen. So if you got the ratio of the mole ratio of the copper and mole ratio of the oxygen, so generally you got the first step. This is the first step you try to figure out. Okay. Well, obviously the mole ratio, when you figure out the number, this number is pretty weird. Okay. Yeah, could be very, very weird. Then we try to normalize the ratio. Okay, try to normalize the ratios. So you try to normalize the ratio. For example, let me just give you one of the examples. Okay, so if you got the copper and the oxygen, the mole ratio, the number you got 2.160. The second one is 1.080. Okay, so how do we do this ratio? The first thing is do not round this number. Okay, you cannot just round this number to a whole number and then figure out the answer. Well, sometimes you're lucky, the result is right, but most of the case is not correct. Okay, so what do? You need to, since you find those two numbers, what you need to do is you find which number is the smallest number, mole number, and then you're divided by the smallest mole number for that one. Okay, so for example, 1.080 is the smallest mole number. So all those two numbers is going to divide by the smallest mole number. Then you can normalize this result. This is a technique to normalize the numbers. Okay, so this number divided by 1.082. And this number also divided by 1.082. So once you divide number, the result give you, 1.080 divided by 1.080. Well, obviously this is 1. And this number divided by this and give you a 2. So now the mole ratio, copper and oxygen is become 2:1. Okay, yeah, so this is how you normalize the result. Once you got the mole of copper and mole of oxygen, the number could be very, very strange. Then you need to normalize those number by dividing the smallest mole number between those two. Then you will figure out the whole numbers ratios. Okay, the whole number ratios. So the copper is 2, oxygen's 1. Obviously, you need to put the 2 and 1 inside of this this formula. Then you go, no, okay, the empirical formula for this case will be just a copper 2O. Okay, so Cu2O. That's gonna be in the empirical formula. That's gonna be the empirical formula. Okay. And last time we talked about, in some cases, when you do figure out the ratio, and you based on this way to figure out the ratio, but your got the ratio is 1.5 versus 1, or you got 2.5 versus 1, or 2.5 versus 2. Well, so now you got this numbers has a 0.5 over there. Then what are you gonna do? I'm saying you cannot run this number, right? You cannot run this number. What do you need to do? You need to multiply by 2 on each of these ratios. Then you will got a whole number, because 0.5 times 2 is equal to 1. That's going to be a whole number. So that's why 1.5 versus 1 actually is equal to 3 versus 2. 2.5 versus 1, you got a 5 versus 2. And the 2.5 versus 2 obviously is a 5 versus 4. Okay, so you can base on this to figure out the whole number. Okay, so this is the special one. This is a special one that you will see in the questions. Okay, this is a special one that you will see in the questions. Any questions? Okay. Okay, so generally this is how we figure out the empirical formula based on the percent composition. And the next part, we try to figure out, okay, how to, based on the empirical formula and to figure out the molecular formula. Okay, molecular formula, and we talk about what's the difference between empirical formula and the molecular formula. Empirical formula is just the ratio between the two elements. But molecular formula is what exactly shows in the molecule. Okay, then so for example, is CH versus C6H6. This is a benzene. This is a benzene. This is a benzene, and this is empirical formula of the benzene. If you look at the ratio, those ratio between carbon and hydrogen is the same. This ratio is 1 versus 1. This ratio is still 1 with 1. 6 versus 6 is equal to 1 with 1. So the ratio between carbon and hydrogen is the same for the empirical formula and the molecular formula. But the difference is the numbers exactly shows in the molecules. Okay, yeah. So to find the molecular formula based on the empirical formula, you need to find the ratio. For example, the ratio over here, the ratio is a 6, right? 1 versus 1, you times 6, you got exactly the molecular formulas. Okay, so the key is how do we find the ratios between empirical formula and the molecular formula, right? We talk about this ratio is easy to get based on the molar mass. Based on the molar mass of the molecular formula divided by molar mass of the empirical formula. Okay, so molar mass of the molecular formula, usually the question will give you the molar mass of the molecular formula. This number, the question will give you. But the empirical formula, the molar mass of the empirical formula, you should find out from the empirical formula. Okay, yeah, for example, you see the empirical formula is a CH. Well, based on what is the molar mass of carbon, what is the molar mass of hydrogen, you figure out what is the molar mass of the CH, right? The CH is in an empirical formula, then you figure out what is the molar mass of the CH. So based on the molar mass of the molecular formula divided by molar mass of the empirical formula, you find a ratio. And then the ratio is going to help you to figure out the molecular formula. You know the empirical formula is CH, and you know the ratio is 6. Then you times 6, then obviously you know that's going to be C6 and H6, because this one is 1 and this is also 1. The 1 times 6 got 6. This 1 times 6 got another 6. So you got the molecular formula. Okay, yeah. So this is how we figure out the molecular formula. Usually, the empirical formula and the molecular formula questions will combine them together. Okay, or they do the separate. Yeah, not sure. Sometimes they combine together. Sometimes they separate. So okay, so generally those type of the question are very, very similar. Okay, very, very similar. I think what else? So this, once we finish this part, we generally work down for the calculation for those mass, molar mass, empirical formula, molecular formula. Then we talk about the chemical reactions, right? We talk about the chemical reactions. For the chemical reactions, we didn't talk too much. Well, first we talk about what is a chemical reaction? What is a chemical reaction? A plus B equal to C plus D. Okay, so we know the first part, that's a reactant. Second part is a product. Okay, and the arrow here is talking about is to form. So we have a reactant A plus reactant B to form the product C and product D. Okay, and we talk about the balancing the equation. Chemical reaction or chemical equations. We try to balancing the chemical equations, and we talk about the balancing equation. Actually, there's 2 steps. First, balance first. Second part is make the whole number first. Make the coefficient as a whole number for later. Okay, so this is how we do the balancing equation. Okay, yeah, so we already did the practice on the balancing part. Okay, yeah, so hopefully you already good at the balancing the equations, the balancing. The most part is you're gonna find the compound that has multiple elements in this compound, And this compound also has a very highest numbers in these molecules. And then you can assume this number as a 1, and then you based on this to balance the other compounds. This is generally what we do, okay? Balancing the chemical equations. And also we talk about the state of matter. We talk about, well, in the chemicals, generally we write several different state, like sodium chloride. This state can be solids. Sodium chloride could be liquid. Sodium chloride could be gas, or sodium chloride could be aqueous. So the different states, they give you the meaning, different meanings. Although these all the same compound, but they give you the different meaning of that. Solids, that means it's just a solid for the sodium chloride crystal. The liquid is talking about this guy is going to experience a very high temperature. So the sodium chloride is melt from solid to the liquid. And gas phases is talking about this guy experience even higher temperature. So, I mean, all the sodium chloride become vaporized, become a sodium chloride gas in the sphere, atmosphere. So this one, I mean, it's hard for you to find this state. But normally in the room temperature, you can see it's just a sodium chloride as a solid. But this AQ means it's aqueous solution, which means the sodium chloride is dissolved in the water. Okay, sodium chloride is dissolving in the water. It's dissolved. Okay, it still is a solid sodium chloride dissolving the water to make a solution.
I was going to set up some demonstrations and some things. I was just going to check and see if we can use a few minutes. Okay, so it's okay if I set up stuff. Okay, just one question. Okay, thanks.
Okay, sodium chloride aqueous, that means this is a solution, and solution we know this is a mixture, right? It's a mixture because it's sodium chloride mixed with water. But those three things are pure substance, right? This is a pure substance. It's just to talk about the same thing. Those are pure substance states. They have solid, liquid, and gas. But the last part is the mixture. It's dissolved in the water. It's a solid sodium chloride dissolving the water. Okay, yeah. So those are the different states. Okay, when we talk about a chemical reaction, we generally talk about those 4 different states. Okay, the last one, aqueous, is a mixture. It's not as same as the previous 3 states. The last part we talk about for this unit is the type of the chemical reactions. So the first one we talk about is the composition or synthesis reactions. Or people call the composition or combination. Generally, it's talk about the same thing. Okay. So it's just A plus B and your form C. We have a multiple reactant, but we are only just one product. So that is the synthesis reaction. And the second one is called the decomposition reaction. Okay, so we have A, then they're going to form B plus C and plus more things. So generally, this one is only have one reactant. We only have one reactant, but we have a multiple product. So that is called a decomposition reaction. Okay, this is called a decomposition reaction. So generally, if you look at those synthesis reaction and decomposition reaction, those two reactions actually is a couple. Okay, so if you go forward, that's gonna be a synthesis reaction. Is go backward, then that's gonna be just a decomposition reaction. So composition reaction and decomposition reaction, those two are coupled to each others. And the third one is what we call the single displacement or single replacement reaction. So this kind of reaction, you can see is just A plus BC to form AC plus B. So if you look at the formula, you will see the A is as an elements, and the elements is going to replace another ions inside of the compound, another ions inside of the compound. And then they're going to replace the position of the B and kick the B out. So the typical things in the single displacement reaction, you will see we have one element. This is one element plus a compound. Then, so this is one element plus a compound. And then they are going to form another elements. And another compound. This is, if you look at the equation and form something like that, you have one element plus one compound. You're going to form another elements and another compound. Obviously, that's going to be a single displacement reactions. That's going to be a single displacement reactions. Okay, yeah. And the last one, no, not the last one. Second last is called the double displacement reactions. Then that's going to be this AB plus CD, and then they're going to form AD plus CB. Okay, so if you look at the chemical reaction like this, you will see most of the cases we have a compound, and especially it's ionic compound. This is compound and plus another compound 1 plus compound 2. And then they're going to form new compound. New compound 1 and new compound 2. And you can see, I mean, A and C, those two replace to each other. So A is replacing the C, and C also replace the A. So they're making the two new compounds over there. So that is why this is called a double displacement or double replacement. Okay, so this is the special one. If you see two compounds in the reactant and also form two compounds in the product, obviously this is a double displacement reactions. Last reaction is called the combustion reaction. And the combustion reaction, most of the cases we talk about is the organic matter. And plus oxygen, they're going to form CO2 plus water. Okay, so this is what we call the complete combustion reaction. There, as long as they convert those organic matter carbon over there to generate CO2, then that's called a complete reaction, complete combustion reaction. And during the combustion reaction, meanwhile they are going to produce light and also produce the heat. So this is a very obvious the way we see combustion reactions. They have an explosion or something. Okay, yeah. So as long as they generate CO2 plus water, that's called complete reactions. Okay, so organic matter plus oxygen. The organic matter, most of the cases we talk about is a hydrocarbon. This is called a hydrocarbon. Or CXYOZ. And this kind of combination, this is called a carbohydrate. Okay, so this is called a carbohydrate or hydrocarbon. Those two react with oxygen, they burn to form CO2 and water. Okay, so this is called a complete reactions. And in some of cases, they also have some incomplete reactions, incomplete combustion reactions. Incomplete reactions is not because of the organic matter, it's because they do not have enough oxygen, and instead they generate CO plus water, or they form to carbon plus water. So if you have the two results, the product generates CO or carbon, then that's going to be incomplete combustion reactions. Those are incomplete combustion reactions. So normally this is what we learned for the whole unit 3. Okay, yeah. So let's take a break, and then we will work on the practice. Okay, we will work on the practice. I print those out, but I do not have a stable with it. So I'm going to grab a stable. If you want to stable them together, up to you.
Like the same. So bad. Oh my God. Yeah, but there was that was a few questions that I didn't. I guess like. You know what? Yeah.